In this video, we will discuss nucleophilic aromatic substitution. We have already discussed electrophilic aromatic substitution, where the ring acts as a weak nucleophile, reacting with high-energy electrophiles, resulting in an overall substitution reaction, which occurs via two elementary steps. The first being an electrophile addition step, where the pi electrons in the ring make a single bond to the electrophilic species, the electron poor species, followed by an electrophile elimination step, where E plus here refers to the name of the step, but really it's H plus that's leaving. That is the specific electrophile leaving. Sometimes that's shown as just H plus leaving. We showed it as the solvent accepting the proton because protons do not fly around. There's always something to accept them, and it's probably a lone pair on whatever the solvent is. All right, in electrophilic aromatic substitution, the ring acted as a nucleophile. In nucleophilic aromatic substitution, the ring acts as an electrophile. Yeah, it's confusing. These names are not from the perspective of the ring, right? They're from the perspective of the species that the ring is reacting with. Typically, not always, but typically, in order for the ring to act as an electron poor species, as an electrophile, it typically has an electron withdrawing group to make that happen. And then the electron-rich nucleophile will react with it in an overall substitution. So in many ways, this looks like the opposite of electrophilic aromatic substitution. I'm not sure if opposite is the right word, but let's get into it now. Let's learn about nucleophilic aromatic substitution. As we're getting started, it's important that you pause and predict the products of these reactions. If you do not think that a reaction will occur, write NR for no reaction and then a brief explanation. So please pause, do this, and then move on to the learning goals on the next slide. The learning goals for today's lesson are to predict the products of nucleophilic aromatic substitution reactions, to draw complete curved arrow mechanisms, including resonance structures of key intermediates, much like we did for the EAS reactions, to explain the formation of products in nucleophilic aromatic substitution reactions. There are two reactions for your reaction chart, and these are general types of reactions, much like SN2 or E2 or SN1E1. Those were types of reactions. So nucleophilic aromatic substitution is a general class, and we can make some descriptions, some generalizations, but you should be detailed in how you describe these reactions so that you can look for them. So these are the two. Let's get started learning about them, and then we will summarize at the end. Here are these reactions that I've already asked you to pause and predict the products of. You probably did not do that, but let's pretend you did. So now you've predicted the products of each of these reactions or assigned no reaction. Now, I'd like for you to revisit those predictions, assign each of the starting materials as either a vinylic halide, an allylic halide, an aryl halide, or a benzylic halide, and then determine if the reaction conditions would favor SN2, E2, or SN1, E1 pathways. Pause and review any of these terms as necessary. Once you've done this, then you can move on and compare with me. We will begin by drawing an example of a vinyl halide. As we know, vinyl or vinylic means directly bonded to the carbon of a double bond. Now, although normal, or they're called aliphatic, where the carbons are sp3, so typical alkyl halides, not vinyl halides, but alkyl halides, they will undergo SN2 reactions with strong nucleophiles. Vinyl halides do not usually exhibit SN2 reactivity. Why is that? Recall that in the SN2 reaction, the non-bonding electrons on the nucleophile attack sigma star CBr. This HOMO-LUMO interaction generates the new carbon nucleophile bond and results in breaking of the carbon-bromine bond. The difference between an alkyl halide and a vinyl halide, or one of the differences, is that if an SN2 reaction occurred on the vinyl halide, it would be occurring on an sp2 carbon. While in an alkyl halide, as we mentioned, the carbon being attacked is an sp3 carbon. Who cares? Well, I don't know, we should all care. The sp2 carbon has a trigonal planar geometry, meaning that this implied hydrogen is in the same plane as bromine, the CH2, and then the carbon atom that it's bonded to. That's not the case for the sp3 carbon in the alkyl halide. That carbon is tetrahedral, has tetrahedral geometry, and so the two hydrogens on the carbon being attacked are not in the same plane as sigma star CBr. One is coming into the plane and the other is going out of the plane as indicated. So SN2 reactions do not occur on vinyl halides because sigma star CBr is blocked by the rest of the molecule. It's all in the same plane. Look at that. Look at these two hydrogen atoms here, right where sigma star is, right where the nucleophile would attack. That's not going to happen. Their electron clouds are there. They're blocking that orbital from reacting with the nucleophile. And so substitution is not observed in an SN2 fashion for vinyl halides. Vinyl halides also do not usually exhibit SN1 or E1 reactivity. Why is that? Well, the first step in SN1E1 is heterolysis, cleavage of the carbon-bromine bond. This would generate a vinyl cation, which is very high energy. And both SN1 and E1 proceed via heterolysis and then coordination or electrophile elimination. Let's just quickly look at that for an alkyl halide. Okay, so both SN1 and E1, again, heterolysis to generate a cation. Tertiary cations are relatively stable for electron-poor cations. Then in SN1, some nucleophile coordinates, right? Substitution, that's what S stands for. Versus an E1 and U might be the same thing as B here, but the species with the electron donor species, the electron-rich species, it deprotonates beta to the cationic carbon to generate an alkene. Okay, so those reactions, SN1 and E1, they do not usually occur for vinyl halides just because the vinyl cation intermediate is very high energy. However, finally, a reaction that vinyl halides might undergo, what product would be formed from an E2 reaction of a vinyl halide? So this E2 reactions require treatment with a strong base, and that base deprotonates beta to the leaving group, beta to the halogen. And in the case of a vinyl halide, as we learned in Organic Chemistry 1, an alkyne will be formed when it is treated with a strong base. And since this particular alkyne is a terminal alkyne, it might continue to react with the base, but we're not worried about that in this scenario. We're just worried about the reactivity of the vinyl halides. So vinyl halides do exhibit E2 reactivity. They rarely exhibit SN1E1 because this is such a high energy intermediate. The activation barrier is very high to form it. Let's just, whoa, high energy, wow, enormous activation barrier. Oh, goodness gracious. Okay, so they do not usually exhibit SN1E1. And they never, ever, ever exhibit SN2. Okay, so keeping that in mind, go back here and make any revisions that you would like to make. After our good discussion, I've made my revisions, and here they are. The first substrate is an allyl bromide, right? Allyl is a double bond and then a CH2 bonded to something, in this case bromide. With an excellent nucleophile, such as a thiolate, we predict an SN2. And in fact, I predict this product from an SN2 reaction. This is an excellent SN2. However, allylic is not the same as vinylic. In the case of the next substrate, in fact, the next three substrates, we have vinyl halides. where the halogen is not bonded to a CH2, but it's bonded to a sp2 hybridized carbon. And there is no SN2 on sp2 hybridized carbons. Catchy slogan, and now we know why. SN2 reactions involve attack of sigma star CX, and in this case, for sp2 carbons, there are other groups and their electron clouds blocking that orbital. No SN2 on sp2 carbons, thus predicting no reaction here. Now, whereas this is an excellent nucleophile capable of a fast SN2 reaction, that is not the case for the next reaction. For the next reaction, there is a weak nucleophile, and what is telegraphed here with the heat and the weak nucleophile is a solvolysis, SN1. However, cleavage, heterolysis of this carbon-iodine bond is highly unlikely because the vinyl cation is high energy. Thus, I predict no reaction. Finally, treatment with a strong base, sodium amide, is predicted to result in an E2 reaction, yielding an alkyne product. Now, if you have not predicted the products for the aryl halides, please do so, and then join me. We've discussed vinyl and allyl halides. Now let's move on to aryl and benzylic halides. An aryl halide can be represented by bromobenzene, where the halogen is bonded directly to the sp2 carbons of the aromatic ring. This is significantly different from a benzylic halide. Benzylic halide does have the aromatic ring. However, there is an intervening sp3 carbon bonded to the halide. In this case, we will choose bromide as an example. You may recall that benzyl halides are very reactive in both SN2 and SN1E1 reaction pathways. However, SN2 reactions of aryl halides are impossible. Impossible. That word was used on purpose. Why do you think that is? Well, I do hope that you answered because sigma star CBr is literally in the middle of this ring. It is surrounded by a bunch of carbon atoms that are in plane with it. It cannot be attacked by a nucleophile. That nucleophile is very much repelled by the electron clouds of all these carbons in the same plane as sigma star CBr. Yikes. So once again, we can chant together, no SN2 on sp2 carbons. We can go back to our predictions, and for these two examples, where there's sodium thiolate, which is an excellent nucleophile, there will not be SN2, okay? No SN2. Sigma star CBr is in the middle of this ring. Yikes, nucleophile cannot attack it. SN2, impossible. SN1, unlikely. So why do SN1 reactions of aryl halides seem unlikely? Well, let's look at the cation that is generated by the heterolysis of the carbon halogen bond of an aryl halide. Well, this cationic carbon has two electron domains, 1, 2. So we would predict it is an sp hybrid. However, sp hybrids are linear. They have linear geometry. That will be impossible without breaking this ring open. So what does it mean if an atom cannot obtain the ideal geometry for the assigned hybridization? Yeah, it's very, very unstable. Now, why again are we talking about SN1 and SN2? Remember, today's topic is nucleophilic aromatic substitution, where there is some aromatic ring reacting with some nucleophile in a substitution. So look, it is going to happen. What we're saying here, what the point of these slides is it is not going to, most likely, it is not going to happen via SN1 or SN2, most likely, okay? Because SN2, impossible. Sigma star CBr in the middle of the ring, not happening. Nucleophile is not like going to tunnel through all these carbons. Not happening. In the case of SN1, it's unlikely because there's this extremely high energy cation. However, it's not necessarily impossible. Are there any leaving groups that might facilitate formation of the aryl cation? Well, like a really good one? We will come back to this question. All right, let's cut to the chase because nucleophilic aromatic substitution definitely happens. In fact, when para-bromonitrobenzene is treated with sodium hydroxide at elevated temperatures, a substitution certainly happens, and after workup, this nitrophenol is isolated. Can you propose a curved arrow mechanism for this transformation? It is clearly a substitution reaction. And hydroxide is a nucleophile or basic species. But we know for sure this reaction is not occurring by SN2, and it's unlikely that it is occurring by SN1. And it's probably useful to tell you that if we had just treated bromobenzene with sodium hydroxide, we would not see a substitution. Most likely, we would see no reaction. So this nitro group is playing a role here, which makes sense since hydroxide is electron rich. If the ring is reacting with it, it is likely because the ring is electron poor. And in fact, hydroxide adds to the ring precisely because the nitro group can accept electrons. Whoa, a lot of arrows, I know. We might not go to this most stable resonance structure first, but once you get the hang of it, you will. And I'm drawing the arrows directly there because this nitro group is the reason why this reaction takes place. It can accept the electrons from the nucleophile. Now, although this is a stabilized anion, it is non-aromatic. And a simple lone pair push, a nucleophile elimination step, so we're reversing these arrows, but instead of expelling hydroxide, expelling the better leaving group, bromide, generates the product. So a nucleophile addition, nucleophile elimination step led to a net substitution. However, just notice there's a workup step, so let's take a step back very briefly and consider why a workup might be necessary. Well, we know that the parent phenol has a pKa of 10. Wow, that's pretty acidic. A normal alcohol has a pKa of 16. So phenol itself has a pKa of 10. With the nitro group, its pKa is much lower than 10 because of the electron withdrawing ability of the nitro. So in fact, in the presence of hydroxide, the phenoxide is generated. And then that workup step reprotonates the phenoxide to generate the neutral phenol. So the observation we can make here is that when there is a strong para-electron withdrawing group, a nucleophilic aromatic substitution results because that strong electron withdrawing group can stabilize the electrons that the nucleophile donates to the ring. This would be the same if there was an ortho withdrawing group. However, for metabromonitrobenzene, no reaction is observed under these nucleophilic aromatic substitution conditions. Why is that? There's still an electron withdrawing group on the bromobenzene. So we might expect that the substituted product would be formed. However, recall in the previous example that the nitro accepted the electrons from the nucleophile via the pi framework. Let's try that when the nitro group is in the meta position and not the para position. It's useful to draw out the nitro group. If it's able to accept the electrons, it will do so via this pi bond. Okay, if hydroxide adds to the carbon bearing bromine, these electrons would move over, perhaps, but they can't go into the nitro group. So we can localize them on this carbon and then try again. Let's draw an intermediate and then try to draw resonance structures. Now we can try to delocalize the electrons into the nitro group, but it is not possible. You can try to draw resonance structures and it will not be possible to show the nitro stabilizing the negative charge. Thus, this anionic intermediate would be high energy, and it is not observed, and the product of nucleophilic aromatic substitution is not observed. The conclusion we can draw from these slides is that an electron withdrawing group, a really strong one, is needed either para or ortho to the leaving group in nucleophilic aromatic substitution reactions. An electron withdrawing group in the meta position cannot stabilize the negative charge as well as one in the ortho and para positions. In fact, only one product is formed in the nucleophilic aromatic substitution reaction of this substituted benzene. Predict the product and explain its formation with clearly drawn resonance structures. There are two potential leaving groups, and it's worth noting that although fluoride is not a good leaving group in an SN2 reaction, it is okay in a nucleophilic aromatic substitution reaction. Thiolate is an excellent nucleophile, and there are two nitro electron withdrawing groups. Recall, however, that for the electron withdrawing groups to accept electron density in the anionic non-aromatic intermediate, they must be ortho or para to the leaving group. A meta-withdrawing group is not effective for accepting the electron charge in the non-aromatic anionic intermediate. Looking at the electron withdrawing groups in this molecule, they are ortho to the fluorine substituent and meta to bromine. Thus, we predict that the fluorine substituent will act as the leaving group, will leave as fluoride. And thus, the product of this reaction will be as drawn. The thiolate group adds to the carbon-bearing fluorine, delocalizing the electrons into the nitro group. In fact, both nitro groups can stabilize the electrons donated by the thiolate. And we can draw the following resonance structure to demonstrate that. Following this nucleophile addition step, a nucleophile elimination step takes place to regenerate aromaticity and expel the fluoride leaving group, generating this final substitution product. Let's now draw a generic reaction scheme for nucleophilic aromatic substitution. Include the mechanism and any notes that you think are important. Give it a shot. This is a short video. You can synthesize what you've learned so far. In nucleophilic aromatic substitution, an arene with a leaving group that is ortho to an electron withdrawing group or para to an electron withdrawing group that is treated with a good nucleophile may undergo nucleophilic aromatic substitution, replacing that leaving group for the nucleophile. The electron withdrawing group, though, must be ortho or para to the leaving group. This proceeds via a nucleophile addition step, followed by a nucleophile elimination step. The nucleophile that adds is the nucleophile that is treated with the ring. The nucleophile that is eliminated is the leaving group that was initially there. Consistent with this general mechanism, excluding the proton transfer steps at the end. Now, the three criteria that are necessary for observing a nucleophilic aromatic substitution reaction by the addition-elimination mechanism are a good nucleophile, such as thiolate, a good leaving group, such as a halide, and an ortho or para electron withdrawing group to that leaving group, such as in these two molecules. Let's summarize the mechanisms by which electrophilic and nucleophilic aromatic substitution reactions take place. In electrophilic aromatic substitution, the ring acts as a weak nucleophile with a high energy electrophile, and overall, a hydrogen atom is replaced with the electrophile. Now, I should note, this does not have to be a hydrogen atom, it just has to be something stable leaving as a cation. For nucleophilic aromatic substitution, the ring will act as an electrophile. And that doesn't just magically happen. There has to be electron withdrawing groups, either ortho or para, to some substituent that is a leaving group. It's stable leaving with its electrons. Right, as we see, X minus leaves with its electrons. And the ring will react with an electron-rich species that will donate electrons to it, since the ring is electron poor with these electron withdrawing groups. All right, mechanisms: electrophilic aromatic substitution. The ring acts as a nucleophile. It donates electrons in an electrophile addition step. This high energy non-aromatic cation is stabilized by delocalization of charge. And if this reaction is occurring to a substituted benzene, we know that the electrophile adds were directed by that group Y. If Y is an electron donating group, then E will add ortho or para. If it's an electron withdrawing group, it will add meta. And we can explain that with additional resonance structures in the case of the electron donating group, and instability of resonance structures in the case of the electron withdrawing group. For example, if Y is an electron donating group, it can stabilize this intermediate when E adds ortho or para, which I'm just showing here for the ortho. Whereas we understood the meta with directing of the electron withdrawing groups in that these resonance structures for the meta intermediate kept the partial positive charge of the electron withdrawing group as distant from the partial positive charges on the ring as possible. From this non-aromatic delocalized cation, an electrophile elimination step occurs where the electrons in this sigma CH bond reform the pi bond and re-aromatize the product. The electrophile that's being eliminated is this proton. And as I mentioned, it doesn't actually have to be a proton. It can be something stable leaving as a cation, for example, a carbocation. Now for the mechanism of nucleophilic aromatic substitution. The electron-rich nucleophile attacks the carbon bearing the leaving group. This nucleophile addition step generates, again, a non-aromatic intermediate. However, this time it's an anion. Once again, these three resonance structures describe how the charge is shared amongst the 4 sp2 hybridized carbons of the ring in this 5-atom pi system. This time there's 6 electrons in the pi system compared to the 5 electrons in the pi system and the cationic intermediate of electrophilic aromatic substitution. Now recall that this reaction only occurs when there's an electron withdrawing group, either ortho or para, to the leaving group. And we're going to go ahead and draw out the electron withdrawing groups just a little bit. We're going to keep it generic and do something similar as what we did in the case of the electron withdrawing group in the electrophilic aromatic substitution example. There is going to be some sort of pi bond, so we'll just draw that out like this. And we can see that the electron withdrawing group will stabilize the negative charge, stabilize that anionic intermediate, and I'll show those arrows in red. But it can only do that when it has an ortho relationship to where the nucleophile adds, or a para relationship. So again, I'm just going to, instead of writing EWG, I'm just going to put in this pi bond because we know the electron withdrawing groups to the pi system have a pi bond adjacent to the ring that can accept electrons. So we'll draw one more resonance structure, and it will demonstrate how an electron withdrawing group para to the carbon that the nucleophile added can accept and share the negative charge, stabilizing the intermediate. And that stabilization is required for this reaction to occur. We did see in the case of a meta withdrawing group, right? Bromine and nitro have a meta relationship here, that the electron withdrawing group is not able to directly accept the electrons as represented with a resonance structure. And so this nucleophilic aromatic substitution reaction did not occur. From this anionic intermediate, the electrons can reform a pi bond, re-aromatize the product, and expel the leaving group in a nucleophile elimination step. And of course, these electron withdrawing groups have not magically disappeared, so let's just put them back in. I hope that this discussion has helped you to compare and contrast the two mechanisms by which aromatic substitution reactions take place. We have one more interesting case to discuss. When orthobromotoluene, which let's just say does not have any electron withdrawing groups on it, is treated with sodium amide. This is a strong base. It can act as a nucleophile as well. Two interesting products are observed. Initially, it might look like a nucleophilic aromatic substitution reaction is happening because one of the products has the amide NH2 and the same carbon that the bromine was, and bromide has left. So it looks like perhaps there was a nucleophilic aromatic substitution reaction. But there are no electron withdrawing groups on the ring. So this is probably not a nucleophilic aromatic substitution reaction, right? The electron withdrawing groups are necessary to accept the negative charge in the non-aromatic anion. And there's another clue. It looks like substitution has happened on the carbon meta to the methyl group as well that doesn't bear a leaving group. And that makes zero sense. So there's something else going on here. It's not it looks like a substitution. It is sort of overall a net substitution, right? NH2 does substitute for bromide, and NH2 does seem to substitute for the hydrogen atom, but this reaction can certainly not be going by either of the mechanisms previously discussed. Here is a sort of clue. When we discussed vinyl halides, we remembered that they do undergo E2 reactions. Now, we don't have a vinyl halide in this case. This is an aryl halide. Nevertheless, upon treatment with a strong base, a really strong base, such as amide, a sort of E2-like elimination can occur and generate an intermediate that we will draw like this. And if we think about the E2 elimination from the vinyl bromide, we can see some of the parallels between these two proposed reactions. However, whereas these two carbons can adopt a linear geometry consistent with sp hybridization, the two carbons in this crazy wild intermediate down here at the bottom, which is referred to as benzyne, those two carbons cannot adopt linear geometry. And thus, this species is more akin to a diradical. So benzyne is high energy, and because it's best described as a diradical, it's also electron poor. It is going to react with the electron-rich species in solution, which is the amide. And both of these carbons are electron poor, and that is why amide reacts with both of them, making either this carbon-nitrogen bond or this carbon-nitrogen bond. We'll draw out both possibilities. Attacking ortho to the methyl group will generate an intermediate that looks like this. This anionic intermediate is also high energy, looks like a Grignard reagent, and will deprotonate the ammonia solvent. Yeah, pretty cool. This reaction is occurring in liquid ammonia as a solvent. And I'll make this carbon-hydrogen bond and generate the product. Now, instead of attacking ortho to the methyl group, it could have attacked meta because both of these carbons are electron poor, right? This species is described as a diradical. I'll show attacking that carbon in green, but either of these pathways can occur, and that's why both products are formed. So instead, it could attack at the metacarbon. That would generate an anionic intermediate like this one. Whoa, high energy, very basic. It will deprotonate the ammonia solvent to generate the product. Both of these pathways occur because both of these carbons of the benzyne are electron poor. So they can both react with the electron-rich amide. This seems unbelievable, but it does occur. It occurs via this elimination and then addition mechanism. So let's draw that out one more time. There's an elimination and then an addition, followed by a final proton transfer step. But recall, this is actually best described as a diradical. Both of those carbons are electron poor. Either of them can be attacked, and both of them, in fact, are attacked, resulting in both of the observed products. Benzyne, very fun. I will briefly underscore one more time that benzyne, as you might expect, is a very unstable species. We did draw it looking a bit like an alkyne, but as we said, it is impossible for these carbons to obtain linear sp geometry, okay? It is impossible because it will break the ring open. Because of that, benzyne is best described as a diradical. Radicals have unpaired electrons, and those carbon atoms do not have complete octets. Thus, both carbons are electron poor. And that is why we observe them both react to form two constitutional isomers of the product, the ortho product and the meta product. This has nothing to do with electron withdrawing groups, electron donating groups. This is not a direction issue. This is that there is a pre-existing substituent that has two different relationships with the two electron poor carbons of the benzyne. So this is not a directing group thing, okay? This is just that there are two different carbons, they can both react, and they have different relationships to this existing group. All right, that was fun. Now your turn. Propose a complete curved arrow mechanism for this transformation. At first glance, this appears to be some net substitution. Bromide is substituted for this, so for the amide substituent. We know that it is not an electrophilic aromatic substitution reaction. These conditions are not one of the 6 reactions that we learned. This functional group is not one that is directly installed by electrophilic aromatic substitution. There's no electrophile anywhere. In fact, these are pretty electron-rich species. Amide is very electron-rich. It is quite basic, keeping in mind the pKa of ammonia, its conjugate acid, which is 35. Speaking of ammonia, we see it is most likely the solvent for this reaction. It's a conjugate acid of another reagent, so typically that just means it's a proton source and it's the solvent. All right, it's not electrophilic aromatic substitution, and it is probably not nucleophilic aromatic substitution either, although that is more likely because there's amide, which is a nucleophile. It is quite electron rich. But it's not NAS because there are no electron withdrawing groups on this ring. There's just this leaving group, but no electron withdrawing groups. So, spoiler, let's try a benzyne mechanism. There's a really strong base, amide, so it seems reasonable, or as reasonable as benzyne can seem, right? Before benzyne is generated, however, notice it says excess sodium amide. It's because this proton on the amide is acidic, and certainly more acidic than the hydrogen that we suspect will be eliminated to form benzyne. So the very first thing that happens is amide will deprotonate the amide. So fun. The electrons in that bond, the NH bond that is not shown, we'll just push them here. Okay, we're going to make like an enolate-like species. where the negative charge is most stable on oxygen. I've drawn out the curved arrows that go directly to the most stable resonance structure, just as we did when we learned about enolates. This anionic intermediate is formed in a proton transfer reaction. Now, from here, need-to elimination of HBr can occur with another equivalent of sodium amide, generating a benzyne. Now, of course, both of these carbons are electron poor. Okay, both carbons of benzyne are electron poor. However, the nitrogen, which we know makes a bond, we can see it in the final product, nitrogen cannot geometrically attack this carbon. It can, however, attack this one. So this will look a bit like an enolate, lone pair push, reform the nice strong carbonyl double bond here observed in the product. Electrons come from nitrogen and make a double bond to the carbon adjacent to the alkyl chain, as seen in the product. That pushes the electrons on to the other carbon of the benzyne, which will generate that anion intermediate we've been discussing. So here's this anionic intermediate, which will be protonated by the ammonia solvent and generate the final product. Good work. All right, be sure that you can summarize what is benzyne, how is it made, what is it useful for? That's a good question. Once you figure that out, let me know. And then how can you recognize that benzyne was formed? I have led you through that analysis on both this question and in this one when we initially discovered that benzyne exists. So really try to summarize on your own and then go back if you need to review those sections and be sure that you've got this down. Before I ask you to do your final summary and fill out your reaction chart entries, let's revisit this slide. We have not really revisited our predictions for the aryl halides, so give it a try. Give it a try now. Once you're ready, let's discuss together. This was a short video, so you have energy. Predict these products for the aryl halides. I agree with what we said initially, which is that even though there's thiolate, there's no SN2 for these first two reactions. And for the first reaction, I expect no reaction overall. In comparison to the second reaction, where there's an electron withdrawing group, para, so in a 1,4 relationship to this bromide leaving group, we have sodium thiolate, which is a really reactive nucleophile, but it's not very basic. So I believe that nucleophilic aromatic substitution will occur on this substrate, and an addition elimination mechanism generating the sulfide. So sulfides are sulfur versions of ethers. Now, if you're wondering, well, why doesn't this undergo a benzyne mechanism? It's because thiolate is not very basic. So it's not going to undergo benzyne. It's not going to undergo NAS. It's just not going to do anything. No reaction. Next molecule, iodobenzene with water and heat. What is going on there? Well, these conditions are telegraphing SN1, right? But there's not going to be SN1 on iodobenzene because that would generate this high energy aryl cation. And for an iodide leaving group, there's no driving force for this. This is a good leaving group. It's low energy, but this cation is really high energy. So no reaction, no SN1 for iodobenzene. And to be clear, there would also be no nucleophilic aromatic substitution. There are no electron withdrawing groups on this ring, and water is not a strong nucleophile. It's a really weak nucleophile, right? And again, there's no benzyne, there's no substitution via benzyne because, again, water is a weak base, so not going to happen, no reaction. Now for this last example, we have iodobenzene again, and then a strong base, much stronger base than thiolate. Okay, so this is amide. It's a really strong base. The conjugate acid of amide is ammonia with a pKa of 35, so really weak acid. versus thiolate, which is the conjugate base of a thiol with pKa's typically about 12. So, amide's only about 10 to the 23 times more basic than thiolate. So yes, there will be a benzyne, so substitution via the benzyne mechanism to generate this aniline. You can try to draw this mechanism out if you like, and double check with me if you have any questions. All right, we're ready to do our final summary. And then overall, what did you learn today? How does it relate to things you already know? Quite a bit, probably. And then what questions you have, let me know. You are able to predict the products of nucleophilic aromatic substitution reactions. You're going to recognize nucleophilic aromatic substitution reactions for all the reasons that we've discussed. There will be a leaving group, probably most commonly a halide. And there will be an electron withdrawing groups, ortho or para, maybe both, to that leaving group. And it's important to say that even fluoride is a good leaving group for nucleophilic aromatic substitution. That is weird because it's not the conjugate base of a strong acid, but it is a good leaving group in this case. And if you want to know more about why that is, you can certainly ask me. All right, let's brainstorm some electron withdrawing groups. Well, generically, in the generic sense, we're going to see the pi bond adjacent to the ring, right? It could be nitro. It could be some sort of acyl group, like a ketone. I'm going to let you think if there are others. All right, and then that aromatic molecule is going to be treated with some nucleophile, some electron-rich species, so good nucleophiles. The example that we encountered today was a thiolate. They're excellent nucleophiles. And then overall, there will be a substitution reaction. Now, when there are no electron withdrawing groups, but there's still a leaving group, and now this is our traditional leaving group because this is in an E2 sense. So basically not fluoride in the case of benzyne. But there's no electron withdrawing groups on the ring. It's treated with a nucleophilic species. And remember, nucleophilic species are often also basic, right? They're both electron rich. So often, not always, electron-rich species can act as both bases and nucleophiles. And you see a substitution like this, but you know it cannot be NAS because there's no electron withdrawing groups on that ring. So it might be benzyne when it cannot be NAS. And so this might even confuse it, calling it NAS via benzyne. Let's just call it substitution via benzyne. So because you are going to spend lots of time thinking about these patterns and doing practice problems and working on your reaction chart, you will have achieved this learning goal of predicting the products of nucleophilic aromatic substitution reactions and benzyne reactions. And we've done a lot of practice drawing these curved arrow mechanisms, and I think you've achieved that goal as well. And if not, you will, because guess what? It is time to practice. Let me know if you have any questions.